Okay, we're going to talk spring potential energy and power, but first, we'll come back to this, especially if you're here in person. Oh, yeah, yeah. I want to make sure I explained this potential energy, change energy stuff this last time. Okay? Energy can never be created or destroyed because of what it is. It's a technique for keeping track of stuff. So if you actually kept track of everything, all the physics stuff, multiplied and added correctly, then you can't lose any energy because it's like a register. It's like money. You kept track of it all, unless someone stole some. Okay, and it's only something like what we'd call that a non-conservative force in physics. Friction would steal some. And it only steals some because we don't keep track of where it goes. We'd have to measure the temperature. Friction is converting this mechanical energy into heat. There's nothing else this chapter that I can think of, so it's certainly not on the test. There's nothing else that takes mechanical energy and then makes a different kind of energy that we usually fail to measure. Okay, but notice the energy is really not destroyed with friction. It's just converted into heat, and so we need the temperature. We need some thermodynamics. That's a much later chapter to keep track of it. So in this mechanics chapter, we would just say that it's lost. So if we don't have any friction, then the change in kinetic energy equals the change in, or plus the change in potential energy has to be zero. There has to be no total change. And we just split those terms. These are final minus initial each time. We split those terms up to get this initial plus initial kinetic plus initial potential equals final kinetic plus final potential. Okay, I really like subtracting the friction term, this little Fk times distance, from the initial kinetic because it's really only if you have friction, then that's where it applies. You have to have some motion at first, and friction takes away from your initial kinetic energy. Because if you don't, then you might have a trick question. Right? If you're not moving, then it doesn't matter. Friction can't do any work if you're not moving, if you don't have initial kinetic. Okay? So far, so good. That's the easy, boring part. Okay. People nodding. The hard part is that, okay, we did work is the change in kinetic energy. That's where energy comes from. We just dressed up our equation 3 back from chapter 2 and such. But the potential energy of gravity, and today of a spring, is minus the work done by that thing. Okay? And that's actually because of how these equations are set up. And you can also say it's yeah, I did. I said that seventh hour. Minus the work that that force could do. We're getting ahead of ourselves in time now, but energy doesn't depend on time. So that's kind of okay. That seems to mess people up a lot. Okay, but try lifting up an object. Okay, its gravitational potential energy must be increasing as you move it up. Okay, because then the gravity has the potential to make it fall. Okay, so as I do positive work and give it gravitational potential energy, gravity is actually doing negative work. Gravity points down, and I'm moving it up. So the displacement and the force point in opposite directions. Gravity is doing negative work going up. So the potential energy as I lift something up is increasing, and it's doing negative work. So negative sign has to be there for that work to have the right direction. Okay, so it matters who is doing the work, like me lifting the pen up, or gravity is doing negative work. And then when I let go of the pen, gravity does positive work, displacement and force both point down, and that gives it kinetic energy back and accelerates it. Yes, ma'am. Well, this is where time and the sequence of events is so important. Because am I in a physics problem? So just me sitting here holding the pen above the table, technically there's no potential energy. You could also say that, okay, I'm going to measure y, my vertical displacement, from this starting point, and therefore it actually has zero now. Haha, mg times zero is still zero, right? You're perfectly free to say that. But then if I have to examine a problem where it falls out of my hand, we have to know what happens. To do an energy problem, we have to know that there's some change. There's to be acceleration. There's to be net force. Or else there's no change in anything, and we're just kind of wasting our time. So time and the sequence of events is important. You have to think about what's going to happen, or what is this problem situation about. Something has to change, or we really can't do an energy problem. Okay, and I'm going to try not to waste your time with that. So when I picked it up, we have to go way back in time. When I picked the pin up and lifted it, I spent some of my chemical, biological energy to get it up there, and I stored gravitational potential energy in it. So I gave gravity some potential energy and spent mine. These rules don't apply especially well to like the workings of a human body. We don't have muscles like a lot of animals do that can hold one position for free. We don't have muscles that lock in place. Some creatures have muscle structures like that, but we don't. So we can't hold still and spend zero energy. We're high-powered, brain-powered mammals, and we spend energy all the time to do basically to do nothing. Which is why your mind and body hates to sit there and do nothing. You have to think. You fiddle with things. You daydream. You're always trying to do something because your body is built to spend energy no matter what it does. So yes, it's technically true that human beings really can't hold still and spend no energy. But for simplicity in these physics problems, we're going to usually talk about machines. And when we talk about people, we do this kind of vague thing where, okay, technically no energy is spent, but really if we actually measured all the heat and chemicals and everything going on, yeah, some would be. Oh my goodness. What a question. When you're dead, are you still working or live or doing energy? Well, yes, actually, the change in energy. There's this other property that we will get to eventually called entropy, and things will always be changing and moving, even if it's not you like willfully doing it. There are still changes going on all the time. We can't really stop them. So I think I'll kind of leave it at that. Yeah. Well, yeah, that's right. Well, are you losing energy? You would lose your heat after you died for sure. It's kind of morbid all of a sudden. Are you losing potential energy? Are you losing your chemical energy? Um, Probably the bacteria in you would make great use of that potential energy and the chemical energy once you stop using it for yourself. So let's not get into who is using what, but the energy is always changing, always moving. Things will always keep changing. It's not, you really can't stop it. And we'll get into that later. And probably next semester I can tell you about quantum mechanics and the real roots of that. Like it can't stop. The universe we're built out of can't stop changing because of like it's the flow of like information or time through the universe. It's just built this way, and so things really can't stop changing. So we are doing pretend problems that are easy to solve with algebra. In case you were wondering, yeah. I can, I'll I'll smash you in the face next semester with a little bit of particle physics, and then you might run away screaming and never become a physicist, but that's okay. Lana, do you have a question? No. Okay, that sounds good. Okay, back to my spring, and I'm gonna have to cut this video, I think. Okay, so we understand work needs a negative sign. So the spring, here I have a spring hanging in front of me in the classroom, and there you can see the meter stick is at the, let's put the low end there. Okay, so the spring starts at about 24 centimeters, and if I hang half a newton, this is 50 grams, so times 10 is zero point 0.5 newtons on it, it's going to stretch down. Okay, and so now the